Yeah, so I've been playing Fortnite recently on a Switch. Don't hate me.
On the Switch. Wow.
That's all I got. I got Mac computers and a Switch. I guess I could play it on mobile, but no.
Well, no, you did PUBG on mobile.
I did
right?
PUBG on mobile. Yeah, I got top 2, and I was pretty happy about that. And I never played it again because it felt like my phone was going to explode. It got so hot.
Right. Yeah, I've played Fortnite, I think, once, maybe twice, but I'm more of a PlayerUnknown's Battlegrounds person myself.
I wish I could play PUBG. I watch YouTube videos of people playing PUBG, and it looks way more, I don't know, advanced.
Yeah, it's more realistic in terms of, they actually have all these bullet physics and stuff gun physics that they put into it, and it's
right.
But it also makes it really challenging.
Yeah. If you want to play with me on Fortnite, my epic name is theHyperfine, as you can maybe guess from this podcast.
Nice.
Yeah, wasn't taken, so I took it.
Cool. Well, yeah, if you want to beat Derek or get your butt beat, then join him.
He'll probably defeat me. I'm not that good. Little 12-year-olds coming in and schooling me every game.
So, should we assume that everyone in our audience knows what these two games are, or should we explain? There's a reason we're talking about this. We'll get there, but should we explain what the games are?
Why is Fortnite and PUBG being mentioned in a podcast ostensibly about physics? Yeah, I think I'll give a brief rundown of what the game is, and then the first part is what we'll start talking about. So the premise of these games, which has kind of become a popular, I guess, type of game recently, is battle royale. So if you're familiar with the maybe 90s, early 2000s, I don't know, Japanese movie called Battle Royale, and its premise, which was kind of like Hunger Games-ish, that there's a whole bunch of people dropped into this area, and it's last man standing wins. So in the movie, it's all these school kids in Japan who are put on this island, and they're given a backpack of stuff, and that's it. And they're just sent out into this jungle island. And the point is to become the last one standing at the end, and you win a spot. In the movie, it was like a spot to continue school or something like that. Like there wasn't enough school for all the kids in this fictitious, futuristic, maybe current Japan. And so they had to fight to the death to see who would survive and go on to continue learning in school, which is a really crazy premise. But that's what it was. And it's actually a pretty awesome movie, but it's very violent. And yeah, these kids are given weapons and supplies. Some are given just a flashlight. Some are given guns. And so you just had to make do. But the kind of interesting mechanic of it all is that they were told to only go to particular areas at particular times. So if there were, 2 people left, they couldn't be on opposite sides of the island and just sit and wait out whatever. They forced the players to go into particular areas and get closer and closer together, so they had to fight, which is kind of the basic mechanic of these battle royale games. And if they didn't go into that area, they would die some way. I think in the movie they had collars or anklets or something that exploded. I think it was a collar.
Yeah, I mean, definitely watch Battle Royale if you haven't seen it. It's a good movie. But yeah, for younger generation, I guess, Hunger Games has the same, there's the fog in Hunger Games where it's like it kind of tries to group everyone together. That way it induces fighting between all the different factions.
Yeah. So Fortnite and PUBG are the current versions of that premise, I guess, in video game form. And I think there is a predecessor. I don't know. I saw a flowchart of how all of these games came to be. And there's H1N1, which was before PUBG and Fortnite, and maybe even that got some predecessor. These aren't the original games that had this premise. The mechanic in Fortnite is there's a storm coming, and if you're in the storm, you start losing damage, and you have to outrun this storm that shrinks. The eye of the storm is shrinking, and you have to continually move to a smaller and smaller circle as the game goes on, and there's fewer and fewer people to fight. But the key thing, and this is what the topic of the episode is, to start Fortnite and PUBG, you parachute in. So you're flying over an island or a small area, and you just drop in at a certain point, and you're dropping in from a plane in PUBG, and in Fortnite, it's like a flying bus. I don't really get where that comes from, but it's like a bus with balloons hovering over an island. And so you jump out of this thing and you can free fall, and then you release your parachute automatically when you're a certain height above the ground. And so what we want to talk about is what's the fastest way to reach a place on the island from the plane or the bus.
Yeah. So to be a little more clear, the plane travels in a straight line across the island. So you might want to pick some area that's not on that line. And so you can't just go straight down. So if you want to jump out sideways, and get to that place, like when do you jump off of the plane to get there? Essentially, it's kind of
right
in the fastest time. And in these games, it's like that's the most important thing, because there's other people that are racing you to that same spot. And if you get there first, you get a gun, you can shoot them and defeat them, and then you have a kill in the game, or you're starting to do better.
Right. Because you jump out of the plane with nothing except a pickaxe in Fortnite to like gather supplies, like you can chop down trees and stuff like that. But other than that, you have no weapons, no nothing. So you really want to be the first one on the ground grabbing a weapon and starting to shoot people. And there's particular areas of the map that are better for finding supplies than others. So you don't want to just drop straight down, which you might think would be the fastest way to get to the ground, because then you have to run pretty far to find a place. So there is some strategy of like the plane's going over this one part, but maybe where you want to land is not directly under the plane. How do you get to that part of the map faster? Oh, the other thing I want to add is the path that the plane takes is random every time. It's a different crossing of the island every time, and it doesn't always go through the middle, but I'm actually thinking of it now. There's some sort of rules written into the program that like it has to start, if it comes from the left side of the map, it has to exit on the right side of the map. Is that true? Like it can never go from the left side of the map to the top part of the map. Like it never cuts a corner.
Yeah. I think it roughly, I mean, I don't know the exact rules, but it tries to travel at least over a certain amount of the actual map. So it's not like it's just going to barely nick,
right,
the edge of the island or something. It's like it'll actually cover, some portion of the island, something at least like that. Right.
So the reason I thought it was an interesting physics problem is it's very similar, and maybe this is where we're going to get into is I was thinking of something like a principle of least time calculation. Like you have multiple zones that have different speeds, and you cross from one speed zone to another. The first is the plane itself, how fast that's going. The other is the drop, how fast you can fall. And the third is the parachute. When the parachute opens up, you fall at a different speed than when you're free falling. And actually, when we just started talking, I thought maybe there's a fourth one, which is walking. But I when I initially conceptualized the problem, I was imagining just landing directly on where you want to be, not the walking part. So I think I want to get rid of the walking and ignore that, which I think would complicate it.
No, I think it should just be, you're going to be a logical person and pick somewhere you can actually get to in your flight time.
Right.
And you want to land there. When do you jump out of the plane to get there the fastest?
Mm-hmm.
Yeah. So you got to where I wanted to end pretty much, or at least the interesting is Fermat's principle.
Mm-hmm.
There's a general equation that every calculus student, or not equation, but a general problem that every calculus student has solved at some point, or at least talked about. And that's like, usually it's described as like the lifeguard problem.
Right.
Which is, a lifeguard sees someone drowning in the ocean and they need to get to them, but that person, they have to travel diagonally to get to them. They're not right in front of them, and they're not just on the shore. So the question is, okay, the lifeguard has to run along the shore some distance, knowing they can run faster on the sand, and then they have to swim to the person to save them. But swimming is slower. So, is it fastest to run until you're perpendicular to the person and then swim to them? Is it fastest just to run to the water and swim in a straight line to them? Or is it fastest to just travel in a straight line, or something totally in between that?
Mm-hmm.
And this is kind of that problem, which essentially reduces in physics to Fermat's principle.
Right. Yeah, in calculus, you set up a function and then you try and minimize it. So you set up a function for the time is equal to the combination of the time in the sand and the time in the water, which is based on the speed and distance. And then you have a function, and then you do some calculus, take the derivative, set it equal to 0 to find the minimum of that amount of time. And it's a pretty simple problem, but it's pretty fun. And like it looks really fancy when you're doing it, but you get a pretty nice answer of like, look, this is the minimum time, and it totally makes sense.
Yeah. Well, and the general problem, I think, is actually non-trivial to solve.
General meaning what?
Like just you have to run, you're some distance back from the shore. You have to run at some angle or whatever you want to run to get to some point on the shoreline. And then you have to swim. Like if you just use the distance you are from the shore and the distance that person is and the horizontal distance between you guys, it's actually a quartic equation that you end up with that you have to solve, which is doable, but hard.
Yeah. A little side note story. A long time ago, I was at Physics RU, and one of the instructors gave a talk on the principle of least time. But the title of the talk was something like, "My dog can do calculus," or something like that. And he would throw a ball in Michigan, and he would throw a ball in Lake Michigan, like we're talking about. And the dog would figure it out. Like he filmed the dog and like found that the dog intuitively could find the least time path. Like he had always hit the mark on how far to run on the sand and then how far to swim. Like he always got, kind of jokingly, he always did the calculus to like figure out the least amount of time. And
people do this. You do this. If you don't even realize it, but you might be walking on two different paths or something, and you'll figure, okay, if I walk up this slope or something, it takes me this speed, and then I can walk on this flat part and I can walk faster. And so like people will automatically, just like the dog, do this.
Right.
Which has actually led, I think, some city planners maybe, or like economists, I think is one of the things I read, to use optics as a way to describe human travel.
Huh. All right. So actually, you just mentioned something, optics. Like how does that fit into what we're talking about? Because it does. Like my brain goes to that place, and I can kind of figure out the connection points. But what is it in your head that makes you think of optics when you think of principle of least time and lifeguards saving drowning people?
Yeah. So I think like we haven't really said what the principle of least time is. We've just mentioned it. Or Fermat's principle, those are the same thing. Mm-hmm. The simplest statement of the principle of least time is that when light is traveling from one point to another point, it takes the path that makes it take the least time. So if you're in air and you're traveling from point A to point B, the path is obvious and straightforward to everyone. It's the straight line between point A and point B.
Right.
But if say you have to bounce off a mirror, then the idea is, light exits A and it has to bounce off the mirror and then go to B. And it could bounce off of any point on that mirror and then end up at B. So what point on the mirror is it actually going to bounce off of?
Right. To minimize the time.
Yeah.
It's always going to find that place.
Yeah. And then I think the thing with the mirror one is that statement there, or that problem, can be said as it's going to take the least distance because the medium is air the entire time.
Right.
So in that situation, least distance and least time is the same. You're solving the same problem.
When the speeds are the same in the whole process.
But now you make it weird. You say, okay, I'm going to travel from one medium, let's say air, into another medium, glass. And it turns out light travels slower in glass than it does in air. So now, Fermat's theorem, you're not going to travel, if you're trying to get from point A in air to point B in glass, you're not going to travel in a straight line anymore. You're going to do some different path that, when you work it all out, it ends up being Snell's law.
Right. So it's like the lifeguard, like it travels further distance in the medium that it's traveling faster in, which is air for light. And then it hits the glass, which is like the water for the lifeguard, and it's going slower. So it'll travel a shorter distance in the slow medium because it wants to spend more time traveling faster. And yeah, the end result of that is what we call Snell's law, which tells you the angle that the light will take when it hits the interface between the air and the glass.
Yeah. And I mean, I think maybe you can like kind of intuitively walk through this a little bit, because I mean, the idea is, okay, you might say, well, light travels faster in air. So just have it go as far as possible in air and then as short as possible in glass. But that doesn't end up being the right.
It's not the fastest amount of time.
That's not the fastest time.
Right.
And then the shortest distance in this case is the line that connects point A and B, A being in air, B in glass. And that's
just a straight line all the way through.
Yeah. And even though that's the shortest distance, it's not the shortest time, which is kind of, that's where Fermat's principle, where he phrases it in terms of least time, becomes important versus like the mirror one that I described earlier.
Right. And getting a little bit more abstract, and I promise we'll get to Fortnite soon after this. This is a specific variation on a broader principle of least action, which is a combination of things. Time is part of it. Time can be part of the action. So there's a general physical principle that I think encompasses like everything, not just light, which is the principle of least action, which everything follows, like balls flying through the air, all the mechanics. Yeah, it's always minimizing a physical concept called action. So we don't need to get into it, but it is a bigger topic. But for light, yeah, it's just principle of least time.
Yeah, which is pretty, I mean, it's kind of a really interesting way to phrase it, I feel like. It's you know, like, so I kind of read a little bit through the Feynman lectures when I was reading about principle of least time. And Feynman kind of says, like, he walks through this example of, you know, what happens when like light, I forget if it was reflects off a mirror or like goes through a lens or something. But, you know, and he says like, okay, you get this data and now we can establish this law that gives you this relationship between what happens here, what happens there. But like, you just have like a description and some math to describe, or you have the world, you have some data and you have some math to describe that data. But that doesn't like help you until you get something like Fermat's principle. That is the interesting physics, is kind of what he's saying. Is like, that's the heart of science, is being able to come up with this general like statement about
the underlying principle that kind of governs all of this.
Yeah, and like a useful thing as well. Like yeah, because like you can make this statement for light, but then you can also, like we just said, use the same math and thoughts for like the lifeguard problem or for Fortnite.
Yeah, so let's tie it back into Fortnite. So the way it's related is, as we said before, there's different quote unquote mediums, which is where you travel at different speeds, and there's certain rules, and it's not exactly an optics problem because there's other restrictions that are involved, but you're kind of doing the same mental calculus as the dog getting the ball or the lifeguard going to the drowning person. You're trying to minimize your time. You have multiple distances and points to change from one interface to the other, and you're trying to figure out, how do I get from this high altitude plane to the ground? And it's more complicated than kind of even what we've been describing, because we have 3 dimensions to worry about. You got the surface, you know, of the ground, and then the height of the plane that you're in.
Yeah,
I've tried just coming up with a general, like, yep, this is the way to do it. I haven't figured it out yet, so I'm interested to hear what you think in terms of just the quickest, always best way to do it.
Yeah, I don't know if I have like the complete rule. Typically what I do is not the optimum, but it's simple and easy. And it works for timing, because usually when I play, I'm playing on a team with friends. And so we usually pick our point. You set a waypoint and you can see it on the top of your screen on a compass. So essentially you know when you're pointed, when you're looking at the waypoint.
Right.
Then what we do is we look down the wing of the plane. So we're looking at 90 degrees to our direction of travel. And we just jump when the angle that we're looking at now aligns with our waypoint. So essentially we jump when it's at 90 degrees. But that's, you know, like we just said, that's not the optimum.
That's not optimum. Right. And I've been trying to figure out the optimum, but that is what I used to do when I first started playing. I was like, oh, it must be when it's directly to the left or the right of the path. But it's not true, because you're missing that time that you're stuck in the plane, traveling not towards your destination, and also not traveling down. You're traveling horizontally. So
yeah. So I mean, I think we can say like a couple of things right off the bat, just from, you know, like looking at like the lifeguard problem is you don't want to do what I just said. You don't want to actually jump out when you're at 90 degrees. You want to jump before that. Because
you want to start falling. You basically want to, like, it's not the biggest distance, but it is a pretty large distance to fall. And you want to be falling as soon as you possibly can to hit your mark. Yeah. If you jump too early, you're going to suffer from just kind of floating in the air and trying to cover a long distance, which is also an added complication to this. Do you know what I mean? Like, the speed you're falling at is not only one speed. It depends on how you tilt your player. Like, you can have them be tilted straight down and you're going to fall way faster than if you don't press anything and you're kind of just floating, like with your arms and legs spread out. So there's variations on the speeds that you could fall with, which complicates this quite a bit.
Yeah, there's actually a like you want it to be the highest velocity you can falling. So before you have your parachute, you definitely want that to be like the highest velocity you can. But then also, if you do let's just make the assumption you're going to wait for the automatic pull, which I think happens at a certain height above the ground for all players.
Right.
Because even though the terrain varies, there's mountains and there's valleys and stuff. Whenever you're like, I don't know, 100 feet above the ground or whatever the number is, your thing will pull, whether it's on a mountain or in a valley.
Right.
But when you pull, you're going to be then, let's say, just moving forward. You want to have your velocity be as fast as possible to get to the spot that you're getting to, which might not be the fastest velocity you could travel.
Right.
But you want you to be ending at that point. You don't want to have to you end up above it and then sink down slowly to your spot.
Exactly.
Or spiral in is usually what people do.
Right. Yeah. So I think it'd be helpful if we just right now just say optimum, what's the best case scenario from the game has started, the match has started, the plane is moving, and I want to hit a place. What's the least amount of time? I don't know the number of seconds, but let's just imagine what the least amount of time is to reach a place. Let's say it's the place we want to go. I think I can work and explain the steps and how to do it. And then I think from there, maybe we could work towards a kind of general idea and concept of guidelines for jumping, when to jump and when, how to move your character.
Okay.
So what I'm thinking is, let's say the plane enters from the bottom of the map, just dead center, bottom of the map, just to get a visual. And it's moving. The plane is moving upwards on the map. So the plane is moving north.
Okay.
The second you're allowed to jump, you see the plane moving for a little while, and then all of a sudden, a couple of seconds later, you can jump. So whatever the soonest amount of time, or the soonest that you can jump, you do actually jump. And then you're going to press up on your control stick, or for me, I'm on a control stick. If you're on a computer, it's different, which will point your character straight down and it'll just bomb your dive. You're just going as fast as possible. Is that moving straight down? I don't actually know. Or is there some sideways movement, even though you're pushing, you're pointed as down as you possibly can?
There might be some sideways movement, but I think it's negligible within a parachute adjustment.
Okay. Right. So let's just say you're at the bottom of the map, the south point of the map. You're allowed to drop. You drop and you fall as fast as possible towards the ground. You're going to hit the bottom of the map. The point where you release your parachute is going to be at the bottom of the map.
Mm-hmm.
Then your parachute deploys when, like you said, you're 100 feet above the ground. Now, the fastest way is you can't just go, you can go straight down if you just don't touch anything on your controller. Again, I'm playing on the Switch. You don't touch anything. You're just going to float down very, very slowly to the ground.
Right.
But, and this is another question that I don't know, if you press forward or up on your controller, you start moving sideways and it feels like you're moving faster. I know you're moving sideways faster, but are you actually falling faster? Is that also true?
Well, so in PUBG, which I can speak to better, PUBG actually has a speed, a speedometer.
Just absolute speedometer, no matter what you're doing?
For the diving part of it, the parachuting part. So it tells you how fast you're going.
How fast you're dropping.
Dropping and parachuting, yeah.
Mm-hmm.
So for it, you do move faster when you press forward. Your parachute leans forward, but now you're also moving forward. So if the point you want to hit is right beneath you and you do that, you'll start moving faster, but you're also moving away from it at this point.
Right.
So you need to do a turn as well. You kind of have to spiral.
Spiral down.
Yeah.
Okay. That was my assumption. I thought that you fell faster if you're spiraling, but I wasn't positive if that was true. So it is true. Okay. And I think it's true in Fortnite too. I'm not positive, but it feels like it is. So you want to be, you don't ever want to just be drifting down. You want to always be moving somewhere. So right. I think the fastest way to get to any place on the ground is to drop immediately the second you can, push forward and just dive your character down as fast as possible. Parachute releases, press forward. You're going to be able to hit a point in front of you. And I think we can think of a circle around where the parachute was deployed. right?
Yeah, yeah.
That's the place on the map that you can actually hit with your character by moving towards that direction.
So you're saying the fastest way to get to the ground is to just jump as soon as you can, go straight down, and then spiral that straight down till you hit the center.
Yeah.
Yes.
Yeah.
Okay.
I think you have like a circle of a certain radius directly under your point where you left the plane.
Yeah. So, I mean, I think, yeah, because there's an interesting thing, I guess, there is like, if we're talking the fastest way to hit the ground, once you deploy your parachute, if you press forward and just hold forward, that I think will take the same amount of time to hit the ground as it will if you spiral straight down.
Okay.
Right? Because I think your downward velocity is the same, roughly. I mean, there might be within a little bit, because I don't know if the velocity is constant, but now you're putting it in a circle, so some of it's going to a horizontal motion instead of a downwards motion. I'm not sure exactly how their physics work, but yeah. So I think from the point your parachute gets deployed, there is a radius, like you're saying, like a circle around that point. That's roughly, it'll take you about the same amount of time to get to any location in that circle.
Right.
Provided you're just holding the forward button down or the controller forward or whatever.
Yeah. So what I try to do is so mentally my strategy, and I don't know if it's correct or not, is I try and picture that circle with the place I want to be at the edge of that circle. That's how I kind of think of it. And I don't know if that's correct, but that is what I try to do. So I start with the place I want to be, and then I imagine that place is at the edge of a circle.
Okay.
And then I try to imagine the place at the center of that circle. That's where I want my parachute to release. Yeah.
So I think that sounds right. I think you kind of jumped a step slightly, though.
Okay.
Or like maybe you didn't jump it, but it's kind of hidden.
Mm-hmm.
So the reason you want it at the edge of the circle, because we just said if you're anywhere in this circle, it takes you the same amount of time to get to the ground.
Right.
So technically, it could be, it doesn't have to be at the edge. It could
be
in
the middle of, yeah. And
okay.
I could have imagined my place in the middle of the circle. And that's also where I want my parachute to deploy. And I would spiral into that point in the middle of that circle.
Right. But then, so the reason you want it at the edge here is because you want to jump as early as possible off of the plane.
Yes.
And so if it's on the edge, then it gives you.
Exactly. So yeah, I'm trying to have that be the far side of the circle from my launch point, because I want to just, get that distance covered. I want to be out of the plane as soon as possible. So I'm assuming the place I'm trying to land is farther away than the closest possible point.
Right.
I don't know that I explained that well, but.
No, yeah. I'm following you so far.
Mm-hmm.
So then the next step is figuring out when to jump, right?
Right.
Yeah. We're of the opinion right now that, okay, it takes the same amount of time to get into a circle once you pull your parachute. So then if you place the place you want to go at the edge of that circle, when do you jump to get there the fastest?
Right. So I got the location is at what I'm calling the far side of the circle. The parachute deploys at the center of that circle. Now I need to work backwards. How do I get to the center of that circle from the plane in the least amount of time? I don't actually know. Because now you're in the like variable falling rate, because you can press your joystick totally forward, but you're not going to hit the center of the circle. I think it's a straight line. Oh, but where on the path of the plane do you jump from?
Yeah, because I think you can think about it like this maybe, is from the center of your circle to the path of the plane, there's a maximum distance that you can jump from to get to the center of the circle, but that is going to involve you falling at the slowest speed. Right,
because moving sideways while falling slows down your drop speed. So we got kind of 3 dimensions to work with, and moving quickly through the up-down direction, like the horizontal, I don't know what you want to call it, not horizontal, the altitude direction, falling quickly through that direction means that you can't move sideways as quickly.
Right.
So if you want to move sideways before your parachute has been deployed, you're gonna sacrifice some altitude speeds.
Right. Yeah. So Man, there's a whole lot to think about
I know.
going on here. So yeah, okay. So what I'm visualizing then is there's a horizontal velocity component and there's a downward velocity component, and you
towards the ground.
Yeah, and you could
That's what
probably
you mean by down. Yeah.
Yes, downward towards the ground. Yeah, you could sum those, or altitude velocity component. Maybe I'll say you could probably sum those, get your net velocity towards the point, and we want to maximize that.
Right.
Is that correct? Okay. Wait. So
first of all, let's just say one thing. It's not like they always add up to a total velocity of blank, because if you don't touch your controller after you jump out of the plane, you have 0 horizontal velocity. You have only downward velocity, but it's slow, right?
Yeah.
If you press forward a little bit, you'll start moving forward in the horizontal velocity increasing, but your altitude velocity is also increasing. And then as you press forward all the way, you're going to dive with your head first with a very large downward velocity, but almost 0 horizontal velocity, if not actually 0. I don't know.
Right. So yeah, I don't know how Fortnite works it out, but I think in PUBG, I'm trying to recall. So if you don't press the controller or touch the keyboard, I guess, it's like skydiving with like all your limbs splayed out.
Yeah, exactly. It's the same in Fortnite. Yep.
Yeah, but you can press forward and you get into this more honed position where you're going to fall faster. But then what's dictating your downward, your what are we calling it? The altitude velocity versus horizontal velocity is the angle at which you're looking.
Right. Yes, that's the correct way to think of it. Like if you touch it at all, you get into like arms and legs tucked and you're like diving a particular direction, either down or forward.
Right.
Or both. And I think what we want to do is get the both maximized. Like it's almost like a 45-degree angle is what we're going for.
Right. And I'm looking at, I'm kind of drawing this out as we're doing it. I think we also maybe made a mistake already slightly.
Oh, yeah. Okay.
Okay. So if we put maybe that's why. That's an interesting problem. So I was thinking about our circle, that you know,
landing circle.
Yeah.
Yeah.
So my thought was like the point where you switch between free fall diving to parachuting would be like a boundary and like an optics problem.
Exactly. Yep.
So that's going to. Oh, okay. All right. I guess that we're still not. Because I was thinking of it. Does it need to be on the edge of the circle? Okay. We still want it to be on the edge of the circle, we think, but we want it to be. It's not necessarily connected in a straight line from the spot from where we jumped from. Does that make sense? So like, let's say we jump out the plane.
I see. Yeah, right. Because yes, I got what you're saying. Because you could, let's say you jumped out of the plane moving directly west. Coming out of the plane, you're going west. Your parachute deploys. Maybe the spot is a little north. If you fall in a straight line directly west, parachute deploys. Maybe you want to turn right and go north with your parachute deployed and hit your target. Yeah,
exactly. Like
that's a possibility.
Okay,
exactly.
Right. Okay, all right, yeah. So okay, no, we haven't made any mistakes yet. It's just that maybe I was getting ahead.
In my head, I wasn't thinking that, but yeah. So what I was thinking actually was to divide the map based on where the plane's path is, to divide the map into different regions, like the absolute furthest possible place you could reach from the plane, and then start bringing in a little bit. I think a lot of things start changing. And I was trying to imagine, like, are there specific regions? Like there's a region directly under the plane where you jump and you just go as straight down as possible. Oh, but you don't want to go straight down as possible because you want to jump a little early and get some diagonal forward motion. Yeah, this is tricky.
Yeah. So here's kind of the way I was thinking. Maybe I'm thinking that we're working backwards, where we start, we pick a spot where we want to go. That's we'll assume reachable purely by flight.
Right.
Then we know that from that point there is a circle that when we pull the parachute, we can travel anywhere in that circle in roughly the same time.
Right.
So then, we're going to say, okay, let's put our destination at the edge of the circle. Then, so the next thing to think about is okay, where is the center of that circle? Because there's actually like a whole bunch of circles that are places on the edge of.
Right.
And also then if we jump from the plane, once we like have picked the center of the circle, where do we jump from the plane to hit the center of the circle in the fastest time?
Yeah, I think I was right in saying that it has to be the opposite side of the circle from, like, if you drew a line on the map from the place where you leave the plane to the place you want to be, I think that's a straight line that you're going to take, and you're going to work backwards from the location you want to be to the place where your parachute deploys, right?
Well, so here's the thing. This is kind of the thing I was thinking about earlier that I was stuck with, is I think if we say that once your parachute is deployed, there's a circle around you that it'll take, provided you can fly well, the same amount of time to get to anywhere in that circle, then all points in that circle are equivalent for our problem, right?
Okay.
So the only thing that matters is the where the center of the circle is.
I see. Yeah. Okay, you're right. Because if the thing is like kind of under the plane, you're going to try and dive as fast as possible.
Or at some diagonal, kind of like you were saying, because you might want to leave the plane a little earlier. That actually depends on what the plane speed is now. Yeah,
but I'm still failing to see a situation where you would want to have the circle's center not on the line connecting the location and the place you leave the plane.
It might work out that way, but I don't think it necessarily has to be that way.
The reason I think it does have to be that way is because when you jump out of the plane, you want to dive downward as fast as possible. Like you want to cover the vertical distance as quickly as you can.
Well, but right? you also want to do horizontal distance.
Yeah, let's go back to my, like, you leave the plane and travel west, and say your parachute opens north.
I think I see what you're saying. You're saying,
or your parachute opens and then you go north. Yeah, go ahead.
If it's on the line that's from the direction you left the plane, assuming you're traveling a straight line, it gives you the fastest down time.
That's exactly right.
Because the horizontal is the shortest.
Right.
Okay.
Yeah.
I'm down with that. I like it.
Okay. I haven't 100% convinced myself, but I'm like 95% of the way there. But I think that's right.
I'm seeing it as essentially we want our down velocity to be as fast as possible.
Mm-hmm.
And so the closer our center point is to the plane, the faster our down velocity can be.
Yep, exactly. Because there's less, like we said, there's like a combination of the horizontal speed and the altitude speed, and you're kind of limited. It's like an exchange between those two things. So the least amount of horizontal speed gives you the most amount of downward speed, I think. I'm pretty sure that's true.
Okay.
So we're trying to fall downward as quickly as possible, but we still have to move towards the location, so we move sideways the least amount we can. So yeah.
Is this then now saying, okay, so it seems like we're saying we want to be traveling downwards as fast as possible. Therefore, we want to have the shortest distance between our center of the circle and the plane.
The path of the plane.
Yeah, which would mean right angle jump.
I see what you're saying, but I don't think that's true. I guess I see what you're saying, but how do we account for the fact that it's actually faster to jump out sooner than a right angle jump?
Well, so okay, I'm trying to think. Is it? I think when we don't include running, when we say we're just landing at that at the spot, it's a little tricky because we're assuming. Or okay, I think there's two problems we could potentially make here. So okay, sometimes there's spots that you want to get to that are so far away you have no choice but to essentially just go as vertical as possible. I mean, as horizontal as possible until it pulls the parachute, and then you just want to keep flying until you get there.
Right. That's right.
I feel like that problem, the way the outcome of that problem is separate from you being able to fly directly to that sphere of influence or the sphere of landing from your. So, okay, that sphere or that circle that we're talking about, that assumes you're just going down, you're forwarding down as fast as possible. You're getting the greatest velocity.
Right.
Then
I think I see our issue is how does the slowest possible horizontal motion, besides just not a horizontal motion, like just not touching your controller, how does that compare to the plane's speed? Like, can you cover more? Can you outrun the plane if you just move forward as far as possible? And do you understand my question?
Yeah. And I think to add to that, though, is it's important to note that when you jump, you don't keep your momentum from the plane. Yes. I don't think
it's as though, yes, that's right. It's not true physics in that sense. Like the plane's momentum doesn't, like, you don't carry it. Like the second you press whatever to jump out of the plane, you're starting with essentially zero speed. I think you have a little bit of downward speed, but I think you actually start with zero speed.
Yeah, I think so too.
Like if you didn't touch anything, the plane would just keep moving forward and you would not move at all horizontally.
Yeah, I do not think you can outpace the plane. At least in PUBG, I don't think you can.
I don't think you can in Fortnite either. Yeah, I think the fastest horizontal hovering of the map is the plane. I thought this was going to be tricky, and it's actually pretty trickier than I even thought. I thought it was going to be tricky, and it ends up more tricky.
So here's what I'm thinking is you can fly. Okay, so that circle that we're talking about from the parachuting, if you can actually jump from your plane and fly to the center of that circle, and then your point is within that circle or preferably on the edge of that circle, that's a different problem. That's essentially, if in that situation, then you just want to jump at 90 degrees to the plane, because once you pull your parachute, you're essentially at your destination. You just have to go down as fast as possible,
right? And
you can reach it. But now, if you want to travel outside of that sphere, say because the point you want to reach isn't within that area, so you've traveled as far as possible, pulled your parachute, and you still can't reach it by holding maximum velocity downwards, then you have Fermat's principle of least time problem.
Right. I agree with that.
So yeah, I think essentially the rule of thumb is if you can get to the location from flying before you pull the parachute, you want to go the shortest distance possible. That way you can get the most downward velocity possible.
Right.
You don't sound convinced.
Well, let's say that the place we wanted to land was directly under the path of the plane.
Okay.
Does that mean you jump when you're directly over that point?
Yes, because in that case, I think we're also making the assumption that the plane travels faster than you do, which I think
horizontally.
Which I think is true. So yeah, you want to jump. Okay, well, no, okay, that is a bit of a Fermat's.
It is, right? Because you want to get that downward distance covered.
But yeah, so you have some horizontal velocity, you can travel fast, but then you need to do a downward one, which is a little slower.
So my assumption and my rough rule is I don't know. I think the quickest way to go from the plane to the ground, like to the parachute opening, is a 45-degree drop. I don't know that that's true, but that's my rough rule of thumb. What do you think about that? 45-degree decline, like you're tilting your character forward, not all the way straight down, which would be 90 degrees, and not totally horizontal, which is 0 degrees, but 45 degrees. There's no rule of Fortnite or physics to make that true, but there is some angle in there, and I let's just say it's 45.
Yeah, I mean, I think there is an angle, yes. And I think you could figure out what that angle is given
doing some experiments.
Yeah, or like you need to know the speed of the plane. I don't know. You might be able to just look that up. I'm sure someone has figured it out.
Mm-hmm.
And then you need to know because if you're going straight down, you can pretty much turn this into a lifeguard problem because you're traveling purely in a plane, right? So it'd be like,
yes, okay, that's right.
Slice it and then rotate it, slice it vertically, rotate it, and you're essentially doing the same thing except this time you're running along the shoreline. You're already at the shoreline. You don't have to run to it. So now it's like, okay, you're just running along it. For how long do you want to run along it before you choose to dive into the water?
Yeah, that's a nice way to think of it.
And that is that's a solvable problem to give you that distance or that angle that you need to try and tackle it from. But I'm not sure what it is without measuring something.
But either way, it's not when you're directly over it. That's for sure. Like we've settled that.
No, yeah, it's definitely not that because you travel faster in the plane. So you want to get, you want to optimize that distance, but then also now you have to travel downwards. So you want to optimize that distance. Just like with the lifeguard problems, it's not fastest to run along the shore till you're perpendicular to your not your victim, your
yeah, the drowning person.
The drowning person.
Yeah,
and then swim straight out towards them.
Right. They're somewhere in the middle. You want to run for a bit and then jump or swim. So you want to be in the plane for a bit and then jump.
Right. And it's probably related to the ratio of the velocities in some.
Mm-hmm. But it's more complicated because the velocity in the quote unquote water depends on the angle that you're moving through the water.
Yeah.
Yeah. So this is really complicated then.
Yeah. Because it's not like a constant velocity in the medium. And this actually there's another thing this might relate to, which is you should know something about this, I hope. F1 racing or just racing in general.
Uh-huh.
There's formulas that people use to maximize the velocity through a track, I believe. I looked it up a long time ago when I was like looking at like racing simulators.
Like an actual formula? Like a math equation? Or like a general principle? Like, I mean, I know the general principle, like hit the apex,
Well, so yeah, it was like...
Don't break into the turn, break before the turn, don't brake while turning, like that kind of stuff. Accelerate through the turns.
Yeah, there's a like, okay, what is the optimum path around a track? And it's the answer, I think, is it's another balancing game where you want the distance to be short, right? But the shortest distance possible, like, so if you're going around like a hairpin turn, right, is the innermost part of the turn. Mm-hmm. So it's really short distance, but you have to slow down a whole lot to go around that corner now. So you lose a lot of speed.
Right.
So in the same way, okay, well, like the fastest way is maybe like going around the outside or something. You can go the fastest, but now you're traveling extra distance. You don't need to travel. So somewhere in between those two is, another least time problem.
Right.
And so I think people have done that to figure out what is the least time path around a racetrack.
Yeah, I think going back to the lifeguard and having the speed be dependent on the angle, call it the angle of attack. I don't know what the word is, but it makes sense in my head to call it that. The angle that you're approaching the drowning victim, like your speed depends on that angle, I think at least makes it a problem that's possibly solvable.
Yeah, it's definitely
I don't know
harder.
What the solution is, but it's there. There is something.
But I think our general principle of saying we want the downward velocity to be maximized can help us because, I guess it's really not the down. We might not want the downward velocity to be maximized.
Right, because we need to cover some horizontal distance.
Yeah. So we need the sum of the two. So you would, right. Okay. Which is dependent on your angle. So yeah, it's it's harder than optics.
It's definitely harder. Yeah. Maybe shifting gears a little bit. I've noticed that when I jump out of the plane, I sometimes move in like a kind of arc path because I can't, hone in my exact target very well. And it reminds me of a bacristochrome problem. Do you know what that is?
Yeah, so you want to get from point A to point B purely under gravitation.
Right.
What is the fastest way you can do that?
Right. Yeah. So what's different about that from what we're talking about here? Like, why isn't the answer follow a bacristochrome curve?
Man, is it? I think it may be because of air resistance in this particular instance, because that actually matters.
Right.
Right. Because it's limiting our maximum velocity.
Right. Yeah. And yeah, the bacristochrome setup, the premise is that it's constant acceleration. So you're continually accelerating like in the gravitational field, right?
Yeah.
So that solution leads to this curve, the bacristochrome, which ends up being cycloids. And you can look up all of the fancy videos that are actually pretty good at showing this. But for us, it's not a bacristochrome problem because there's not constant acceleration. Like you jump out the plane and you are moving at a constant speed given your fixed angle. Maybe the solution is to change your angle? Ooh, what do you think of that? Like you falsely create a bacristochrome problem. I don't even know what that means. But.
No. I think that might be because we've only been discussing traveling in straight line paths.
Mm-hmm.
There probably is a solution that you want to maximize your velocity throughout this path, which might not be straight line. You might want to start off really steep and then level out or something.
Mm-hmm.
And in which case it might be more like a bacristochrome or some other arc, which is like a whole nother level.
Right.
To this problem.
But it's interesting that the way the bacristochrome was first solved, as far as I know, I think it was one of the Bernoulli guys who did everything. But one of them visualized the bacristochrome problem. Like imagine a point on your wall, like high up towards the ceiling, and another point towards the floor. Not directly under it, but off to the side. And what they did was divide in slices on your wall, different speeds. And the one above it was the slowest. The one at the top was the slowest. The slice at the bottom was the fastest because you're accelerating downward the whole time. And take a whole bunch of slices and increase the speed with each slice as you move down the wall. And then take the limit of infinite slices, which is the continuously accelerating. So the bacristochrome problem is essentially a whole bunch of Snell's law problems, interfaces, changing speeds, but then taking the limit as those go to infinity, essentially having infinite interfaces of increasing speeds. And then you build up to the continuously accelerating or constant acceleration, but accelerating the whole time, bacristochrome. So I'm wondering if the fastest way, when given the option of programmable speeds of those slices, is the fastest way the bacristochrome. Like start with the slow speed at the top, but increase the speed as you move through the different layers. No, that would be the opposite though. Yeah,
you'd want to start for it to be more like bacristochrome. You want to start steep and then level out as you go.
But that's not the same thing because starting steep means you're moving the fastest at the top. But in the bacristochrome problem, you're moving the fastest at the bottom. Is that true?
Yeah, see, so I think you're kind of saying like why this is not necessarily the right answer. The other issue I think with a bacristochrome, the reason it can't be that is a bacristochrome, you have to actually travel up at some point.
Oh, you're right.
Like you travel beneath your destination and then back up to it.
I forgot.
And we are limited by the ground.
Do you have to though? I know that you can. I know that's like part of it, but can't you just pick any parts of the cycloid and have that be your bacristochrome?
I am not sure. I'd have to like resolve it and look at a bunch of bacristochromes.
Right. Yeah, I don't know.
Yeah, to know if that's always the case or not.
I think to tie a bow on this, I think what we're saying is this is really complicated, but yeah, I actually can't tie a bow on it. I don't know what the general takeaway is. You want to jump, not when you're directly above it. You want to aim at somewhere that's maximizing the downward and horizontal speed as needed. Travel down as quick as possible and horizontal as fast as needed. Shoot for opening your parachute a distance away from your location and try and just coast as fast as possible horizontally with your parachute to hit that location. But I don't know I don't know how to pick where to jump out of the plane. We haven't really tackled that, except that it's not a right angle So I had this question and I was like, oh, I bet people on YouTube have figured this out. And I searched and it's not figured out. Like people don't, there's videos that say this is the fastest way. And one of them said jump as early as possible. I'm like, well, that's definitely not true. I mean,
yeah,
it is in some respect. No, it's not though. You don't want to jump as early as possible because you want to maximize the downward speed. If you jump as early as possible, you're having to move horizontally a lot. So it is a balance.
Yeah, I mean, I think the real like kick in the crotch here that's making it like extra challenging is this variable velocity.
Right.
So like, I mean, with the optics problem is you just have one constant velocity and another constant velocity. Mm-hmm. And so the fastest way to travel between 2 points in any one of those mediums is the straight line connecting those 2 points. So that's simple. It's straightforward. For us, though, that's not. We have a variable velocity.
Dependent on the path.
Yeah. Situation. So that's why I was saying it's kind of like, I feel like it's kind of like the race car thing, but I kind of Googled that a little bit and I couldn't find a good explanation of it. Maybe this is something else we can think about a little more and try and get back to, because it's.
I think this is actually a good problem for like a numerical solution. Like just program the rules and then let the computer figure out what the fastest way to get to each place is. And I'm imagining the results are going to be like these stripes or like this gradients of like when to jump and where. I don't know. As you move away from the path of the plane.
Yeah, I'm trying to think about. I mean, I think like the thing that we could say, if we knew the speed of, like, let's say you're doing the one where it's right beneath the plane, the speed, you want the ratio of the speed of the plane to the speed of your horizontal velocity. I'm not sure if it's just horizontal or your velocity in general, to be a ratio of the sine of your two angles. Is that true? No, I think it's weird because you're traveling at 90 degrees. So you're like, you don't have like this angle of incidence is 0.
Right. Well, I think we'll leave it as either you or me, or maybe a listener wants to write up a little simulation of how this works and try and figure it out, which would be pretty cool. And to leave this, I think we've been working under an ideal situation of completely horizontal land, but it's pretty important in actual playing of the game, which I'm totally going to do right after we stop recording, that you want your parachute to open as low and close to the ground as possible. And we said, I think you alluded to the fact that trees and hills, like there's terrain to take into account. And so you do want to shoot for a place that has not a hill, basically. Like you want to have your parachute open at a lowest point possible.
Right. Like, so like one of I think the best examples of this is there's a area in PUBG on Erangel. That's the first map that they released, called the prison.
Right.
And it's a prison surrounded by it's like a prison at the bottom of a little canyon. And so like when you jump there, you want your parachute, like if you're diving towards it, you want to be above the actual prison which is at the bottom of the canyon when your parachute gets pulled. You don't want to be at the edge of the canyon which is a lot higher.
Right. Because you want to be as close to the ground. You want to maximize the travel time in the air, because that's without the parachute, because that's the fastest you're going to be moving. So shoot for parachute release at the lowest point. But it's complicated because you got to be high enough to clear the edge of the canyon, but then you got to be low enough in the canyon to pull the parachute.
Right.
Yeah. Same thing in Fortnite. You got the divot and then also the loot lake as lowish points, and there's a river with the canyon. Yeah. So shoot for those places, or in the river situation, I try and like travel along the river by looking at the little overhead map and try and make sure I'm above that lowest point of the river while I'm flying. So hopefully get my parachute to open at the lowest point possible. And then I come out of the canyon with my parachute open and hit, Tilted Towers or something, which is on the kind of rim of the valley of the river. And then that's the other reason why everyone drops on building rooftops, right? You don't drop on the front door of a building. You shoot for the roof because you want to not be using your parachute as quick as possible. Like get out of your parachute,
right?
Start looting as quickly as possible.
Yeah, provided that there's stuff on the roof.
Well,
or you can get down from the roof.
Stuff on the roof, or you start hacking away and break into the roof. There's no hacking in PUBG, right?
Nope. Well, there's a lot of hacking, but not
there's no
not
pickaxes to break
destroys.
through roofs, right? Like if there's nothing on the roof, you got to go through a stairwell or jump off the roof to get into an open window or something.
Yeah, sometimes there's holes in the roof you can fall through, but you can't create a hole.
So Fortnite, you just hit a roof as quickly as possible and start hacking as fast as possible. Yep, good times.
Cool. All right. Well, so we'll either write this up or think about it more and get back to you, because we thought we were going to be able to just kind of wing this a little bit. At least I thought I did. I was like, oh, I'm going to look up some Snell's Law
exactly.
stuff.
Me too. It's way more complicated than I thought. And that's why there's no videos explaining it. They give you like the general jump as early as possible and like shoot for the low areas, which are good tips, but they don't capture the whole situation.
Yeah. The only thing we could say is don't jump as early as
but
possible.
Don't jump as late as possible either. It's like a Goldilocks.
What that Goldilocks is, I think it's doable to figure it out. Like we just need to start by making maybe the assumption that you travel in a straight line and work from that. And then from there, release the Kraken and let you travel in some curved path.
Right.
But I think most people travel in straight lines, so that might be sufficient. It's just, so at least your velocity is constant along that straight line, but every straight line connecting the 2 points has a different velocity to it.
Yeah. And now I'm just remembering something I watched in one of those YouTube videos where they said Fortnite updated. Like, it used to be that you traveled faster by spiraling, or I think they said switchbacks. Like, that was faster. That was a faster way to descend than just holding straight forward or something like that. I don't know if that was true, but they updated it to where it's not true, or they made some change. No. So it's, even if we work this out, the algorithm, the mechanics of the game could change and completely make everything we said irrelevant. So it is a game, and it's pre-programmed by people.
Right. Yeah. And it's not real life. Yeah. There's, like we said, I think when you jump out of the plane, you don't carry the plane's velocity.
Yep.
But okay, well, we'll work on it and try and get back to you.
That was fun. Yeah. Join me on Fortnite at theHyperfine.
You could try and find me on PUBG. I think that works. My username is Snortis.
Snortis?
Yeah, nice. Snortoise. That's a tin tortoise.
Ah, I get it. Nice.
Dudumtis.
Cool. All right. Well, I will talk to you soon.
All right. Happy playing.